Sure.
Now remember, there is no C or E.
There's just FA.
There's just FA. Yes. So we're going to start with a single factor model with a standardized factor. Sound good? Meaning we're going to estimate, we're not going to estimate the factor variance, we're not going to estimate the factor mean. What we need to think about with the factor model are what are all the parameters and how we're going to go and give them priors, effectively. Ben.
What is your basis for using a single factor?
My basis is, I don't know where to go with these data. I would actually go a step further and say that these, prior to this, the person I received these data from described that they would just add up the items, and so it seemed like there was a single factor. They were built with the understanding they measure a single factor. But you were going to.
Well, yeah, I just wonder, right? There's you could wonder if there's a single underlying factor of craziness, like Lisa suggested.
I would go, even though, like in private, I would say that let's do this from a clinical version.
Sure.
Somebody who believes in conspiracy may not be crazy,
right?
For whatever reason. Let's
Sure.
just go and say
absolutely. So
tendency to believe in conspiracy, or
Yeah.
these conspiracies. Really, is really what I'd say.
there could also be other factors like racist leanings and things like that.
Absolutely, absolutely, and some of these items, I don't know that these items. I mean, these are pretty terrible things to even say out loud, but that could be really. Could that be comorbid?
Right.
With it, right, in kind of a clinical. I'm trying to do this as scientifically as possible, rather than just as, like, this is an interesting example, and the Denver airport has a mile of tunnels underneath of it, you know, where they. Seriously, go look up the airport conspiracies.
It's like Illuminati stuff.
Oh yeah. Oh, here, I'll just do it. There we go. Conspiracy theories. Several conspiracy theories relating to the airport's design and construction, such as the runways being laid out in a shape similar to a swastika. Murals in the baggage claim area have been claimed to contain themes referring to future military oppression and a one-world government. It's actually kind of morbid. There's like bombs falling, and there's kids and whatnot. And here, let me go this other. We'll go with the Independent. There we go. So outside the airport, as you drive out, there's this Bronco, and it's got these crazed eyes, like it's red eyes that are right there. It's like a demon. It's really crazy. Let's see here. So there's creepy art and strange decor. I don't want to subscribe. This is one of the things. It said it was built by the New World Airport Commission. And nobody has been able to establish the existence of such commission. This is like on it's like I don't know, whatever stone this is in the airport itself. It's the Illuminati's headquarters. Adding fuel to the fire is the date of the dedication, March 19th, 1994. If you add those together, you get 33. The highest level one can achieve in Freemasonry, which represents perfection. It's a $2 billion airport. It's hiding fallout shelters. There's the airport runway structure. The thought looking like a swastika. It looks like an airport. You need to have north-south runways in Denver. But yeah, there's a whole. This one doesn't show the pictures, the murals that they had there. Maybe Mashable does here. No. Let's try this. Bronco runways like that. Dedication stone. Oh, there thinks there's a mysterious network of underground bunkers underneath the airport. So it turned out, I think this in the construction of it, they built this elaborate baggage system underneath that they ended up having to scrap because it never was functional. And then, I don't know if they rebuilt it or did whatever, but here's some of the murals. The fire, the children. Like, peace and harmony with nature is meant to address the destruction of the environment. Children of the world dream of peace. Nope. Yeah, and then this. That seriously, that is a mural in the airport. I kid you not, right? I remember getting my bag when AERA was there, and walking by this and being like, "What the?" Like, yeah, Auschwitz. Oh my goodness, yeah. And there's the Bronco on the way out with these crazy red eyes and whatnot. So yeah, Denver Airport conspiracy. So anyway, I was just brought this up casually because we were in Colorado and everybody flew through the airport. Like, did you see this? Yes.
I want to be real. After this class, I will remember nothing of CFA, but I'll remember everything about that.
Could you also remember EFA sucks?
I will also remember that.
Maybe you just call it SFA, which is sucky factor analysis. Sorry. I'm just kidding. I'm trying to like building hyperbole, really. That's my editorial review letter when I send it out. Like, this study sucks. All right, let's do this. We need to figure out the distributions for these things. The cool thing about factor analysis, in many respects, is that we did that already because we did linear models, right? So we did regression. We struggled for what the priors were. Turns out, this right here, for factor analysis is nearly identical to regression. Now, mu is just beta itself, right? But, and actually, I got this wrong. I wrote this wrong. This should be, the conditional model has the mean of the factor in here. I should know this. I'm doing a research project, and I generated my data wrong because of that. So, but when you look at this here, this is multiple regression, right? This is the same structure of multiple regression. So if we were thinking about what a prior for mu and lambda might be, you might think, what were my priors on the betas before, right? Seem plausible? If you were thinking of a prior for what the residual variance in regression was, but in our case, unique variance, would you start with inverse gamma, like we did before? Seems reasonable, doesn't it? Okay, yeah, let's go with that. So then the question is, what's a prior on the factor? Well, we already stated it. Right here, right? So for us, when we do this, because we have a single factor model, it's just univariate normal. And because we're going to identify it with a standardized factor metric, it's just have a mean of 0 and a variance of 1. So that's the prior for the factor. Not bad, right? That seems pretty quick. This is why I tried to spend more time with linear models, because they're sort of the foundation. But we get linear models right, we get Bayes from psychometric models. But there's certain catches. So I'm going to create analysis here. We have 10 items. We're going to run 4 chains because 4 sounds wonderful. The Illuminati told me 4 was good. 3,000 iterations, 2,000 of which will be burn-in because the Bronco had the orange eyes. I'm just going to start saying crazy conspiracy. And if we have an adaptation phase, remember the adaptation phase is where JAGS is trying to make the Metropolis algorithm be more efficient, right? So I'm going to, it by default starts with 1,000. I'm going to let that run a little bit longer. I firmly believe in a good adaptation before you start to sample. And then the thinning interval, I'm just going to allow it to be 1. Remember, thinning is how many step iterations are we discarding, right? Or how many, what is the number of iterations we're keeping, I guess. So if we have thin of 1, we're keeping every 1. Thin of 2, it means we take every other 1, right? Thin of 5 means we take every 5th one. And sometimes we want to do that to reduce autocorrelation. But if we run the chain long enough, it's not going to make a difference. We're going to be fine with it. So any questions on this so far? Is the font big enough? Can you all see this okay? Awesome. For the mean vector for all of the items, if the linear model we did before, we set the means value to 0, the intercept, because we had no idea what that would be. We know for each of these items, though, the mean has to be somewhere between 1 and 5. The data are between 1 and 5. I didn't show you the data, but let me do that real quick. Here's the numbers, right? 1, 2, 3, 4, 5. So I just picked the mean in the middle. But I'm going to say the prior, so this is my prior mean of 3. Is that good? Is it bad? Well, it depends. My prior variance around the mean, I'm picking to be 1 million. So would you call this an informative prior?
He's informing me that you don't know what will be.
Exactly. And then because JAGS is JAGS, I'm going to go switch variance to precision. And I'm going to let that be 1 over the variance. The factor loadings here. Now, this is where it gets interesting. There's sort of a debate in Bayes, but I would actually say the debate happens much before Bayes. When you do factor analysis, I learned to allow your factor loadings to possibly be negative. There are people who say, no, absolutely they can't be negative. So is 0 a lower bound versus 0 being a mean? And there's two sides to that. We're going to see them both in what I'm about to happen. So have you learned before factor loadings or in IRT that discrimination cannot be negative? Have you learned that? Is that where you believe? Or are you like, let it be negative? Some people believe both. Not believe both. Learn one way or the other. When you learned CFA, were you told factor loadings can be negative?
The items will be reverse scored.
Could be reverse scored. Alternatively, they could just be really terrible.
Yeah.
It's diagnostic in some way. And that's where I allow it to be negative for me. When you learn IRT, like a unidimensional IRT model, a 2PL with a discrimination, do you allow that to be negative when you learn it?
I get it.
Okay, so it depends on I felt like a lot of times if you learn more of the when I grew up, psychology's version of CFA, where you allow the factor loadings most often to be negative, it's okay, then the psych version of IRT, the item factor analysis, is just an extension that keeps it there. Whereas I feel like if you're really housed in the ed world or some of the IRT camps, then you might be like, oh, no, A's have to be positive, we're going to keep them positive. Why this matters for us is when we start to set a prior, if we're going to lump lambda with mu and keep them having a multivariate normal prior, we're going to allow it to possibly be negative. So that happens. Okay.
Do you have a question about
Yeah,
that?
please.
So, to allow something to be negative or not, you will do it in the way that where you set your values or how you set your distribution for those priors.
Okay, so setting the values, so it's more the distribution, but it could be with the values as well, right? So if you think of, we could set, so for us, we're allowing, if we allow it to be normally distributed, we're allowing half of the distribution potentially to be negative, and that's okay. Setting the values, if we were to say, oh, the mean for lambda is -1, that might lead to something that's very different. But this is actually going to cause us our first hurdle with doing factor analysis coming up here. So I'm dwelling on it now, foreshadowing there's going to be a problem coming up here.
Label switching?
Almost.
I mean, because you have to, right?
Identification of another type that we never talk about.
Okay.
So with mu and mu variance, because of the scale, we have a maximum possible variance for the distribution of mu, right? And it's certainly less than a million. Yeah?
Oh, right, yeah. Well, it depends on what the variance of f is. Now, we're going to fix that to 1.
Sure.
But yes, there will be a maximum, and we could lower that down for the mean.
But
certainly.
Functionally, if we took it to be the maximum possible variance anyway, this is still doing the same thing, but more of it.
Right, exactly, yes. It's sort of saying, if these were, I think I'm setting this up under the auspices that our data actually are continuous.
Mm-hmm.
Like if these were like regression type data, then we wouldn't have a maximum variance for it, right? It'd be disentangled. It'd be related to what the variance for the factor happens to, but not necessarily specifically related.
Sure, I guess we're assuming multivariate normality anyway.
Mm-hmm.
Like, it can have as big a variance as you really want, but just our actual measurement scale was. Yep.
No, that's a really astute observation. I think that's really the key, and what I'm hoping to get you to think about when you're setting your priors are what is a good spot for it, right? When I was going through, if you read the book chapter 9 setup, you'll see the variance that is picked is usually like 10 or something much smaller. And I'm trying to build it from, I want to build it from the buildup of linear models. I really want to dwell on if we can do linear models, we can do measurement. That's sort of where I get to. But it's a really good point. That's really overkill for what the variance should be for this, particularly when we know our data are bounded.
No, the we're treating is not bounded, right?
That's exactly right. Exactly right. So I'm treating this. The other flip to that is when we get to IRT, none of this is going to change, right? This part right here changes. This stays the same. Actually, this goes away. This changes, right? So if that's the case, then these might be valid priors in IRT as well. It's really where I'm leading this to be. What is the bounded variance of a logistic distribution? That's a tough thing to figure out. So it's like, well, when in doubt, just make it big. Uninformative is what I think about. A good question. Other questions on prior choices? I always feel like this is the part where it's like when you see your presents for your birthday, if you have presents on your birthday, like your gifts, and they're wrapped. But first you've got to talk to people. It's like, oh, I'm thinking of our son's birthday is coming up like next week, and so. Oh, but I just want to open the present. I just want to run the model. No. We got to think through the priors. Right, that's what the present for me is the analysis. Totally there. I want to get there. But we really have to. If we don't set the priors up right, we're in trouble. And we're going to see there's another thing we're going to be in trouble for. The unique variances. Remember the trick we did last time? I said let's set the degrees of freedom to something very, very small, like 1, and then let's set the variance of. Like the prior variance to be the variance of the unconditional, the marginal variance of the data, so we have this nice wide range in theory. So I did that as well. This data vector is what we load up to send to JAGs. So these are all the things that I'm going to reference in my JAGs code. And actually, let me get to the code first. And of course, I had copied and pasted because I had a snafu with my. So it turns out, as I was doing this, there are certain models of factor analysis in JAGs that it just stumbles over and it takes forever to run. And so in that, I had to kill R, and I was afraid I was going to lose all my progress, and so I just copied and pasted. But when you copy paste quoted text, it doesn't keep the indentation structure. So that's frustrating. Let's go with the syntax here. Okay, so previously in regression, we had a loop over people to put the data likelihood in. But we didn't have a loop for item. So the difference in this is now we have to, for each person, we have to go over each item and express the likelihood of the data for it. And here I'm expressing it with respect to a univariate normal, since we're going through each item. I could have bundled them all together and done multivariate normal, but that's going to bring up a conversation we need to have a little bit more time for. In particular, we need to talk about what the prior distribution, well, we'll get to that. A little bit more. I wanted to show this as well. There's a few more steps in multivariate normal to get JAGs to cooperate. It's frustrating. It can be frustrating, so try to limit that. So here, the mean for each item is given by mu for the item plus lambda for the item times, I put x factor for the person. I put an x there because if I'm tracking the factor variable, JAGs will alphabetize the variables as they come back, and F puts it above the lambdas, and if I want to look at the parameters, then I have to sort through all the factor scores to figure that out. So I'm putting X on it because I want to put it at the end of my variable list if I ever record it to begin with. Right? But, so in this code, similar to what we saw in our regression code, actually it's a little bit different from our regression code, I'm putting all the means into a vector. Right? So mu now, I put in brackets which item it applies to. And the same thing with lambda. Instead of having each lambda be separate, I'm putting those into a vector as well. So I put brackets to say where that is. And the same thing with the factor. The factor is a vector It has 177 people in it, so I can tell which person that is. So we create the mean for each item, which is mu plus lambda times the factor. We create, then we go and say this item itself, in my data I'm calling it x. Now here I'm saying x is a matrix, so I'm going to be passing a matrix into JAGs. Whereas previous, in the regression example, I named each of the variables so we can keep track of them. Here I'm just lumping all the items into one big X matrix themselves. The reason why I'm doing that for us is because unlike in the linear model before, where we had that model.matrix we had to go use to get our design matrix, we don't really have a design matrix here. We're not passing that, right? We're just going to plug in items. We could have a design matrix, but we're not doing that right now. Questions on this so far? So X is a matrix. The rows are, people are down the rows, and items are across the columns. So this is going to be a 177 by 10 matrix. And if I go show my data to you here, and when I load up the data to put into JAGs, I tell it it's equal to conspiracy right here. So this is just this big matrix of all the items, right? So person by items matrix. So it's one of the nice things about this is that you can pass matrices just as well as you pass vectors to JAGs, right? Questions? So what this has done, this first part of the code right here, we have expressed the measurement model. We've expressed the data likelihood here. Now we have to go in and put priors in. So the first prior we end up doing, I'm going to end up touching is the factor. Because this prior is a little more complicated than we've seen before in that we have to take this factor vector and say for each person, so for each entry in that vector, we're going to say the factor is normally distributed, univariate normal, rather than multivariate. And actually, this is the place where I didn't want to do multivariate, because if we end up having more than one variance, we got to specify a prior for that, and that's where things get crazy. Not bad, just harder. So this, every person's factor score follows a univariate normal, mean of 0, variance of 1, or precision of 1, pardon me. Hate that part. Questions on that? Okay. Then we go for our other priors as well. Priors for items. These are our item parameters. We have our mean. We're saying each item mean is univariate normal with a common mean, prior mean, and a common prior precision. Now we set the prior mean to 3, the prior precision to 1 over 1 million. Same thing with lambda. And now remember the one catch is in linear models, the error variance was we had to do the inverse of the variance, 1 over the variance. So this inverse side, this is our inverse unique variance, is a gamma distribution. And it has the 2 parameters. Now here, because each item had a different variance, the prior beta is a vector that I'm passing it, right? That has each of the items' variances in it. So why am I doing that? Remember the prior distribution for the variance, I'm setting this weird prior based on degrees of freedom and prior belief about what variance should be. And I said the variance belief that I talked about in the linear models example for the last couple of weeks has been, let's just set it to what the maximum variance of y would be. Not explain variance as the maximum, as a conservative measure, because then we'll have a lot of, it would be fairly uninformative relative to what it could be. So when I pass this, what I did here is that I went and I used the apply function to get the variance for each of the items. So this is each item's variance that I'm passing it to build that. And that means when I form psi beta 0, this is our prior gamma distribution beta parameter, it differs for each of the items. How are we doing?
In the I just don't remember.
No problem.
The margin equal 2 is what is making the apply go over the columns, no?
Yeah, that's right. So, pardon me. Let me explain that. So in R, taking the variance of just the data frame itself won't push the variance across it. So the supply function says I give it the data, and I tell it take variance across either rows or columns shows up here. And so this is columns, right? So this is the variance of it. If I had changed this to 1, I would get 177 versions of variances. Actually, probably blow up. Oh, it computed the variance for each person. But yeah. You're welcome. Sorry about that. I try to not do apply a whole lot in teaching, but sometimes I sneak it in to, I don't know. R is apply. What do you like apply in R? Those of you who do tidyverse? Is apply tidy then? No, I'm just kidding.
Not really.
No, it's not part. It's base. That's right. I dream in base R. Okay. So one thing. Let's see. Did we get everything else? Okay. So once I set the priors for all the parameters, then I'm just going to go and take the inverse unique variance and convert it to 1 over it to just get the regular unique variance back. Okay? Question?
Question on the prior distributions for the factor.
Yes.
X factor and then person. Is it a prior for each person's factor score?
Yes.
Okay.
It's
But not a prior for the factor variance as a thing.
not yet. It's because we've identified the model where we've set the factor variance.
Okay.
So in a Bayes sense, the factor variance is what we call a hyperprior, because it is a hyperparameter, pardon me, because it is one of the parameters of a prior distribution. So a hyperparameter in Bayes refers to a mean or a variance of a normal distribution that's a prior, right? So in our case, factor has a prior distribution that's normal, so the normal parameters are hyperparameters. The 0 and 1 are hyperparameters. So if we were to go and estimate the factor variance, if we were to do a different type of identification, then that hyperparameter would also get a prior.
Okay.
And that is what we would call an empirical prior for F, rather than this is sort of a hard-coded fixed prior for it. But
We don't need a prior for the factor variance because factor variance is 1 no matter what.
in this model, yes. In just 5 minutes or 10 minutes from now, we will absolutely need that.
Okay.
Other questions? Are we ready to let it run? Now, I'll note I'm leaving out, so in the parameters I'm saving the mean, mu, saving lambda, factor loading, saving the factor unique variances, and the deviance, where the deviance being sort of the log likelihood of the data evaluated each iteration with those parameters from that iteration. And then I'm not saving X factor here because plotting things, I'm going to throw away the factor scores until I know the model runs. And then I'm going to come back, and if I want them, I can save them. But basically, keep those out because otherwise your objects get really big until you've got everything working. The other part of that is the R2 JAGS package, which I actually like because it makes it, I don't have to specify as much stuff to pass to JAGS. I cannot get the seed to allow me to have the same chain with the same seed. So I've stayed away from that for now, but then when we need to get to something more elaborate, I put it in the code later on. Okay, so here's model 1A parameters. I set the seed. This is syntax that's very common for the seed itself. Have the syntax. I'm going to run the GLM module. Now I'm going to tell you something about this. Why I structured it this way is because I really want JAGS to think I'm running a linear model, because I get an efficiency for the linear model that I wouldn't get if it goes other than that. Right? It's going to start doing conjugate priors in a linear model. So that's why I load the GLM package or module. I load the DIC module because it'll allow me to get deviance tracked or monitored through the chain. And now we're ready. We're going to submit our model to JAGS. And it compiled. And you'll note it didn't adapt. That's actually interesting because that means we succeeded in not having to need a Metropolis algorithm. Right? If we tripped it into to having one or more parameters where we were using Metropolis for, it would adapt. You'd see a little progress bar come out and be computing, basically trying to figure out efficiency. And we can actually show list samplers of model 01A JAGs. Come on, Templin. I said EFA sucks. No, really, Templin sucks. Typing. This is telling us for each what version of MC algorithms being run in JAGs. So when we see conjugate, that means Gibbs sampling, generally speaking. So we see a bunch of conjugate normal, conjugate gamma. That's good. GLM generic, that also is good. Want that to happen? So it's all conjugate, GLM generic, it's all good stuff. That means this will be most likely a very efficient chain, which is why the Illuminati told me 3,000 iterations. Can I just say the Illuminati will tell me this? That means...
What's Illuminati? I don't actually know.
There might be a little bit of bias for that. Okay, so now we're going to draw the samples. This is the Markov chain we're actually going to run. You're going to see a progress bar running. It takes a little bit longer, and that's because we have a lot more parameters. Each of the factor scores is a parameter. And this is a big difference in estimation from what you may be used to for using ML. In ML, we have this nice multivariate normal distribution for the marginal data, and we use it to figure out how to quickly go and find parameters. We have no factor scores at all. And the way this is coded in JAGs, it's not using that marginal data likelihood, it's using the conditional data likelihood, which means factor scores exist. Now, there would be a way to code it marginally. I worked on that to show an example, and then I dropped it because to get there it took a lot of doing. Yeah, it's a mess right now. So it ran. Okay, should we see our convergence? Uh-oh. Look at those numbers. This is the Gelman-Rubin for the 4 chain. Each of these point estimates is essentially the ratio of weighted within between versus between chain variance of the parameter. 1 is where we want it, is like the ideal. And the deviance is 1. That's our log likelihood. So if we just looked at log likelihood, we'd be like, oh, it works. Wait a minute. 1.53, 1.54. What's up there? Have you seen that in the examples you've run? No, this brings up the hassle, the first hassle of what we have to deal with. In that, and here, I'm going to plot it. I'm going to try to plot it. Let's take a look at some of these parameters. Okay. Oh, what happened? Figure margin's too large. Is that because too small? Oh, well. Okay. This is where we're going to have to plot a little bit more directly. I'm taking a look at what this object is. It's an MC list. Okay, so an MC list is fairly easy to work with. The Coda package plots MC lists. If I do apply or lapply, the way that you have to go and extract parts of this list to plot individual parameters is a bit more complicated. We use the lapply function, meaning we're going to go and apply something across each of the list members. So in this case, And the function that we're going to do is we're saying function of x, and we're going to just return, in this case, x, and we're going to bring out one of the columns of it, right? So in this case, I think I can plot, like let's column 2, I think is the first factor loading. So if I do plot of that, it should just give me, nope, that's not working either. What did I do to ruin my data?
Doesn't know what to return the function.
Yeah, it's a list. Oh, that's right. I see. So I need a plot.
In the way that I will do it, I will put the plot after function x, so we know, because you are basically hard coding the function inside.
Yep.
the data like here.
Try that. Like this?
Something like that.
Yeah.
That
No, what I was trying to do is I wanted the lapply to send back a list, but to have only one variable in each.
Oh, you wanted the list.
A list of one.
Okay,
Yep.
Now I got you.
Yep. And so because of that, now I've got something else wrong. Let me see if I can overwrite my object. This is frustrating me. So typically when I see that message, it's because I'm projecting this and I'm not getting the right size margins. So let me see if it's something I've done also. All right, hang on one second. So, how's it going? There we go. Okay. Here's where I want to get to show you what's going crazy here. What's up with these lambdas? Nope. Yeah, all sorts of craziness going on. That didn't go so well, huh? Yeah, Tuesday, right? All right. Remind me to tell you all when I took my 3-year-old daughter to Mardi Gras. That's a great story, too.
He's not kidding. That happened.
Awesome. I should have taken Huey this year, so I could rite of passage.
It's not too late.
True. So what's going on here? Turns out, go ahead.
Well, it looks like they're starting to get there, right?
Yeah. And I'm not seeing what I had seen before. When I had plotted this at home, I had seen something really descriptive of what the problem, emblematic of the problem. And actually, the resolution is just too far out to see. Maybe I can zoom in real quick. Let me see if I do this plot. Yeah, I can't do that. Okay, but what's happening here is we've tripped over one of the problems with measurement models. In that, it turns out there's 2 modes to the likelihood function. Right? Think of it this way. If you have the factor that's positive, right, or better yet, if all the factor loadings are positive, and a factor f, that value that you'd plug in for the mean is equivalent to when all the factor loadings are negative and f is negative 1 times f. There's a real big mode issue, right? So what am I trying to say? Depending on where we start our chain, depending on how it samples, we might see multiple chains, one of them going to where all the loadings are positive, one of them going to where all the loadings are negative 1 times themselves. And if we had tracked the factors on the negative side would be negative 1 times the factor. There's more than one mode that we get into.
And having a giant variance
Can do
make
that.
that worse.
That can make it worse.
Yeah.
And the question in building Bayes models is this a feature or a bug? Right? Because there's some models you expect multiple nodes. When we get to mixture models, they're everywhere. But when it comes to factor analysis, you don't expect that. Have you ever heard that before? The likelihood, there's more than one solution to the likelihood if you allow the loadings to be negative. And this is what precipitated the conversation about negative loadings. Right? So what's happening, because we have that big variance for the lambda, and because we're not specifying to JAGs how to sample lambda or how to start sampling lambda. Typically what happens in the Markov chain, particularly for Gibbs sampling, because you don't have a proposal distribution, is the side that you start on is the side that you start to move toward, kind of like an EM algorithm or a typical optimization algorithm. So it's possible, and actually I believe this is happening here, although you can't see with the resolution of the graph, that our lambdas are going to different modes. Right? And if I were to be able to zoom in, which I can't, even though these look like they're coming to a point, the scale of the y-axis is so big that it's hard to really see where that happens to be. They're just massive numbers.
So we could either shrink the variance significantly, or we could tell it what initial values to start with. Right?
We could. And those are very, very nice ways of thinking of it. The other thing we could do is make sure one of the items is positive, or identify it slightly differently.
And do we want to do that?
Yeah. And there's a reason for why in just a moment. But I want to note something, though. Look, this is what you see here with these values. Here you go. You can start to see it with the lambdas themselves. Here's the quantiles. Here's the summary of it, right? At the lower end of it, you get the negatives. At the upper end of it, you get the positives. But they're also massive, right? They're not where they need to be. The other part of it is the deviance, right? This is the log likelihood. If all you looked at was the log likelihood, you'd never know this was happening because the log likelihood's working the whole way through, right? It's the same log likelihood. You're just on one mode or the other. So this is one of the reasons why deviance sounds like an awesome idea. I wish we could just have a single convergence. And actually, if you think about it, ML has a single convergence criterion. It's effectively deviance. You're optimizing effectively deviance. And not exactly. There's a likelihood function, proportionality.
Each chain is converging.
It is. It's converging to different modes. In some models, people say, well, the modes is information. I may have a multimodal distribution. I want it to converge in different places. But for us, we know that this is a bug. This is not something that we want for factor analysis, right? Questions on this? No, bad, huh? I left it in there because you'll note, here actually I can also do this after the burn-in period, and it's still bad, right? I cut off the first 2,000 of the chain. So how do we fix it? So my first pass was exactly what Ben was saying. I thought, oh, let me just go and shrink the variance of the factor and go and specify some starting values. But then and that would get you there. It could get you there.
But shrinking the variance goes against the principle of I want it to be uninformative, and selecting values seems mostly equivalent to saying let's have one of these be positive.
Yeah, that's exactly it. So there are some problems with it. The other problem with this is if we generalize, and at the end of my example, which we probably won't get to this week, but we'll get to, I think I'm going to make this a little bit longer. If that's all right. We're in psychometrics though, right? We're okay with that? We're okay with it. Yeah. It is what it is. I'm going to keep talking about conspiracies and fill up time. It's not Bayesian psychometrics. It's the Illuminati talking to you. The other thing with it is when we get to two factors, right? We could identify two factors in the same way. We'd have to specify means of 0, variances of 1, but then we estimate the covariance, the correlation, right? And for two factors, that works pretty easily. We could specify a prior and a correlation to make that work. But when we get to 3, it's a lot harder. Because with 3 factors, now we have 3 correlations, and they have to combine to be positive definite, right? With 2 factors, a 2x2 correlation matrix is always, so long as the correlation is between -1 and 1 is positive definite. When you get to 3, there are ranges where it's not going to be invertible, right? And that's where problems happen. So what you end up seeing is the specification of prior for multivariate normal distributions. The conjugate prior for that is a generalization of the conjugate so the conjugate prior in multivariate normal for a mean vector in a covariance matrix. Right? We saw a univariate normal. The univariate normal prior was normal for the mean, inverse gamma for the variance. When you have more than one mean and more than one variance covariance matrix, it's multivariate normal for the means. It's the generalization of inverse gamma for the covariances, which is called inverse Wishart. So an inverse Wishart prior shows up. An inverse Wishart prior, like our gamma or inverse gamma prior, we can specify sort of a initial guess as to what the covariance matrix might be, but it doesn't allow you to do it in a patterned way. Meaning if you have covariant correlations, there's a pattern. There's ones down the diagonal of your covariance matrix. You can't use an inverse Wishart to generate that matrix. So much more commonly in Bayes, when you're dealing with psychometric models, when you have multivariate factors, you have an inverse Wishart for the covariance matrix. Now JAGs, instead of covariance, instead of variance, it's precision. The analog of that is instead of covariance matrices, it's inverse covariance matrices, which means it's a Wishart distribution. We're going to get to that next time. Talk more about that next time. But what I'm going with this is just doing the standardized factor is nearly impossible when you have more than two factors in a psychometric model, because that prior that you typically specify is not going to give you not going to sample the correlation matrix. It's going to give you something that's a covariance matrix. And so for our models, we have to use a marker item to identify them for the factor, the variance side. Does that make sense? Well, we'll see that part coming up. So what that means is we're going to have it much easier right now, and we're going to see it generalized much quicker if we just go with a single item. We don't change anything else, we just change it to a marker item. Sound good? How we doing? Questions? Is this nuts or what? So now you're thinking to yourself, why does anyone do Bayes for CFA, right? It's ridiculous. Look what we have to think about. I did a quick, standardized, when I do my own stuff, I know the standardized item stuff. Standardized factor identification is going to work really well with ML, right? I know what I'm going to get. Marker item usually works pretty well, unless, of course, the item you pick to be the marker has no relationship to the factor. That's the one catch. Right, the loading should be 0. You fix it to 1, and everything goes, what? So anyway, so let's go and specify that. I'm going to use all the same specs from before. I'm not changing priors. Not changing any of that. But now I have to specify a variance, a prior variance for the factor. Right? So instead of saying f is, before we had normal 0, 1 for f, right? Now it's going to be normal 0 sigma squared f. So I have a parameter here, and I've got to now give it a prior. This is what we're going to call empirical Bayes prior on the factors themselves, because we're estimating the hyperparameter of it. So I'm going to go about saying, hey, it's a variance. I remember variances from last week. I used inverse gamma on the variance, which means 1 over is precision, which means JAGs will look like d gamma. Cool? So what is, in using that same trick, I know the expected df, the degrees of freedom, I'll just set to 1 because it gives me a very uninformative version of it. What's the maximum variance of a factor? Depends on which item's the marker, right? You think of that beautiful slide that Lisa created here. And I've lost it. With the matrix right here. So this is what you call the predicted covariance matrix. This is the marginal version of it, the data here, right? So for any one item, if we pick item 1 as the marker item, then the variance of the factor is embedded there. So we know the variance of the factor is really, right? The loading goes away, it's like a 1. So we know that the item variance has to be factor variance plus unique variance. So as a maximum, it can be is if unique variance is 0, then it's, the factor variance as a maximum can be the item variance. Start to make sense? This is where Bayes is starting to test your knowledge of model, right? You have to sort of go and plug in things and, okay, well, what is this? What is this? What is this? It's really easy to be like, oh, I can do this. I know Bayes, and then have it completely blow up. Like I didn't expect the standardized factor. I've used Bayes a long time. I didn't expect the standardized factor to blow up like that, by the way, this week. So that's what we're going to do. We set the factor variance. I'm going to set the first item to be the marker item, just because it's a sort of a convention. Technically, I could set any of them to be, and I could always go and standardize my results. But now the syntax for this is going to look very similar. The only thing I'm changing in syntax is under the factor line. So again, I have my model up here. Nothing's changed about my model likelihood. For the prior distribution for factor now, instead of having a 1, I'm actually estimating the fact. I put in the factor precision. It's a new parameter, right? Pardon me, there is one difference in the model, but you don't see it in my syntax because of the way I'm doing it. The first item's lambda I'm fixing to 1, which means I actually have to specify it in my, when I get to the prior for it, I'm not going to give it a distribution. I'm going to set it equal to 1. And then when I go and input my starting chain, my random number seed, I have to make sure that we have a starting value of 1 for all the lambdas as well. Lots of stuff, right? Okay. Question? Okay. So now, so for each item, again, the mean is still the same prior from before. The inverse unique variance is still the same prior from before. But now I get down to lambda, and I'm setting the very first lambda equal to a value of 1. And then the rest of them, from 2 all the way to capital I, in that vector of them, I'm setting the same prior from before. Right? Then I get to the prior for factor precision. It's gamma, right? The gamma, 1 over sigma squared has a gamma prior with our alpha and beta that we calculated before based on the maximum variance that the factor can have. And then I'm saving factor variance instead of the factor precision, and I'm saving the unique variance as well. Questions on the syntax? So we'll just run all this. Here is my new data. Now I have to give it a new set of data because there are different things that are showing up in what I'm doing. In fact, this factor alpha and factor beta have to be in there. And now when I go and run my model, when I initialize it, you'll note it's actually doing adaptation right now. And where it's adapting is the factor variance. That one parameter switched it over for the factor variance. Now we have no longer a Gibbs sampler, we have a Metropolis sampler. And that's actually given right here. So everything else looks the same. So most of what we have, most of the samples that we're drawing are coming from Gibbs. Still going to be pretty efficient. Have I lost you? Have I gone too fast? We're going okay? Okay. So now we're going to sample. Takes about the same amount of time. Here it goes. So, anything you learned today? It's harder, right? This is harder to set up a CFA model than it is in an ML sense, right? I learned that Bayes sucks.
We kind of see that in 2 cases, right? They're kind of the same cases we think about as linear models. Like ML is easier and quicker than linear model. Like,
Absolutely, yeah.
Way less thought has to go into it. So in that sense, not a lot is necessarily gained.
Right.
With Bayes.
Right. It's sort of what are you going to use it for? Why are you doing this? If you're pooling data, I think that's a good one. If if you have to use priors of some sort, if you have if you're worried about small sample size issues. But let's see if this worked. I'm actually just going to take the post burn-in version of this and take a look at my, oh, there it is. Leading order of 3. You've seen that one? Doesn't that make you mad? It makes me mad. Turns out, I believe that actually happened not because of multivariate, but because we have fixed lambda 1 to be 1 the whole time. So this syntax right here strips takes everything but lambda 1 to give that to you. And there it works. And take a look at those convergence numbers. That's what we're looking for, right? So that's the nudge the factor model needed to just become identified, to be on the right direction of the mode. One item being positive throws the rest of them heading toward, for the loading, throws the rest of the loadings having to go to the mode that is in positive direction. If we made it -1 for that factor marker, you see it go the opposite direction, actually. Interesting stuff, right? This is the other feature of Bayes that I came to learn. I learned a heck of a lot about the rest of statistics, including frequentist and ML, through Bayes, because I would never think about multiple modes in the likelihood function. I would never think about what the model actually happens to be. That's like your first step, right? There's a lot you have to do. Now, I will note, some of the issues that we're dealing with here is because we're using JAGs. There are way cooler ways and quicker ways to develop your own code to do this very same task much more efficiently. But the price we're paying for using a general package is that it's trying to be as efficient as possible, but there are ways where it's not doing it. Not great. And one of those ways for us is stumbling over how long the syntax has to be. By comparison, M plus, if you switch estimator equals Bayes. You don't change your M plus syntax, it will figure all this stuff out for you. So if you've got a very regular use case for us, if we were doing CFA, always, it may speed your time up to not worry about JAGs being, I'm going to run every possible model, and it's going to narrow it down to one very specific model, and you code it yourself. So if I'm telling you this from the perspective of if you're working on a project, usually it's the people in quantitative dissertations or theses, they're developing models or doing something new, but you're using Bayes. There's a trade-off at some point where it's a lot longer, it takes a lot longer to run ML. If you think of the number of times you have to run an algorithm to start to finish, it may end up being quicker doing something on your own rather than the other way around. But okay, let's take a look at the results then. Look at that. Those are the quantiles. There we go. Deviance. Don't know what that should be. It's kind of like a log likelihood. Factor variance. Good. Got our item loadings. Have our means for every item. Have our residual variances. And it converged. I'm not showing you the plots because I'm tired of plotting on the screen, but you can imagine what a plot looks like when you have the Gelman-Rubin of 1, right? They're pretty much on top of each other. One or more may be a little bit wiggly, but that's not. And just again to show the Gelman-Rubin statistic, they're all 1.0 or 1.1.
Maybe very stupid question.
Not at all.
And you don't have a question. Is a way that you can get your discriminant function result from here? Or
What discriminant function are you wanting to get? I don't know if I know what
you
that
know
is.
when you do, for instance, CFA under Emily, you can get your discriminant function, and then from that you can get.
Yes. So your fit function, your minimum function text statistic.
Yeah.
Yes.
Yeah.
So we're going to cover that, and we're going to cover that next. So hold on, it's not a stupid question at all, but the answer is pretty stupid.
Okay.
Smart question. I've got a really dumb answer for you, but we're going to get to that in just a second.
Sounds good.
But that brings up the next question I'm going to ask you. But other questions about this right now. Do you think this is converged, first of all? All right. So in Bayes, sorry, let's back up. CFA, what I think about with respect to when do I get to go and open my present of results, right? And I've always been told, okay, analysis, did it converge? Check. Same thing here, did it converge? Yeah, that's really good. We want these to be less than 1.1 or 1.2. This is really good. This right here is the way you want it to look, okay? So it converged, great. Typically, like last week with linear regression, we said, great, let's open that present, let's see the results. But in factor analysis and in psychometric models, there's another step. You can't open the present and look at the results without looking at model fit. Did this model fit the data? Because if it doesn't fit the data, you got to return your package. You got to go and just like, nope, my present, I can't open it. Sorry, kid. You hit mommy, so you don't get to have. Sorry, this is the conversation we have occasionally. By occasionally, I mean like all of this week. And no, actually, not the present conversation. We're not threatening him with that. Sorry, kid. You don't get a birthday this year. You're stuck at 3. Forget it. All right, so there we go. We could also compare the deviance values. Here's the other neat thing about this. Again, from another point of view, this is model. I've blanked on where I was going. No, I don't have the deviance I was looking at. This is, I must have written it. Oh well. So, does the model fit the data? Great, and that's where the question you want to usually go is, right? Because typically in CFA, the way things get taught or get worked is that we have this, to go and figure out our model parameters, we have this kind of discrepancy function, right? Is that what you were mentioning, right? Mm-hmm. And so under ML, the function is sort of some combination of our model implied covariance matrix versus our saturated model covariance matrix. And I hesitated there because that. We could do the same thing here. However, what is our saturated model covariance matrix? What's a saturated model? So in ML, you're like, oh, okay, so I'm just going to go get my MLE for the covariance matrix. I'm going to compare that to what my model implies is. And then that gives me, unlocks like a chi-square, like a likelihood ratio test, whatever. But think of what I just said. I'm going to take a Bayes result with a posterior distribution for a covariance matrix, and I'm going to compare that against an MLE. That makes me feel very bad. It's done, and in fact, this is where I got really grumpy last week. I mean, I get grumpy a lot. Don't talk to me about EFA. Spills out, right? Don't hit daddy. We don't hit, right? In Bayesians, you've never seen a Bayesian love ML more than in model fit. I kid you not. And if you read chapter 10 of the text, you're reading about posterior predictive model checks. Now, chapter 10 actually goes and says for every step in the chain, we can form a covariance matrix, and then we can go and plug in the MLE for the covariance matrix and get a discrepancy function value, convert that to a chi-square, and we can see how the distribution of that is. Yes, we could do that. But what are the properties of that? What are the properties of comparing a Bayes version versus an MLE? That seems odd to me, particularly when we have 177 people in our sample. That's probably not going to work too well. So that's where I get kind of grumpy in that, come on now. The saturated model is a model. You can estimate that in Bayes. You can come up with 2 versions of covariance matrices. What's the right one? Right? Really, shouldn't you be worried about the posterior distribution of the saturated model's covariance matrix and how this one compares? But you don't read that. I looked in 2 or 3 different places to find this, to find something different. I haven't seen it, but it could happen, right? You see where I'm going? So I have to give you the crappy version of model fit. I'll just say it, right? This hurts me, right here. The other part of that, you'll see the posterior predictive model checks in the book in chapter 10, we're going to go and form effectively a correlation. Like we're going to look at every step in the chain, we get our our model implied covariance matrix, we're actually going to generate data from that, and we're going to go and take the correlation matrix from that data, right? Well, that correlation matrix is MLE, right, as well. But then after that, then we're going to compare it with the correlation from the data, not the posterior distribution, the correlation from the data. So it's a mess, is what I'm getting at, right? It's sort of this mix of Bayes versus not Bayes, and all the premise thing, all the things that people talk about for why Bayes is so pure and good and awesome. Well, yeah, that's right, but we need to see if model fits. So we're just going to go back to ML for that. It sort of happens. But, all right, should we see if this tries to fit? We have like 4 minutes. Any questions? Actually, I'm not going to bring up model. We're going to leave this here. Let me talk about one other thing. I had assigned another homework. I've got good news for you because I talk so much and I really wanted to hate on EFA. Actually, it's not because I wanted to hate on it. I'm trying to give you my perspective about all the measurement models and stuff, right? I was going to assign homework today to be due in 2 weeks, and the homework is on the server, and it's a factor analysis. You can go find it. There's 2 problems. There's one that's find an article again, write up be a reviewer. The second is here's an analysis. Analysis you're not going to be able to start yet unless you follow this all the way through you can. But I'll just delay that due date by a week. Sound good? But that means I can't give you 7 homeworks this year. So my present to you for that is that 7th homework you get all the points for. Okay? Sound deal? Like a good deal? Education is forgiving. It's where the consumer wants less of the product. Am I right? So, does that sound cool? So, for next week, if you want to follow along in the book, we're on chapters 9 and 10 loosely. I'm really trying to give you there's a lot of good stuff in those chapters, but I'm also trying to give you like, okay, yeah, but here's what I would say. Yeah, but here's what I would say. So trying to blend the work of the authors with the work of what I'm thinking about too. And in the process, be thinking about how model fit might work. All right? All right. Any other questions or comments? We're finally in Psychometrics. Have a good weekend. Have a good rest. See you next week.